Thanks, Liaba. This is joint work with Aviv Yaish, Zhang, and Kartik Nayak. And I'm going to be talking about how transaction fee mechanisms are actually affected by parallelism, and especially in a model where transactions don't execute as the user intends always. Today's talk would mainly be a motivation towards why transaction fee mechanisms should look into parallelism and consider parallelism into its design. Okay, so let's look back 5 years and let's look at how execution used to look like. So consensus was slow and the execution of transactions took very little time. So we didn't really try to optimize the execution time, and many of the researchers here in the audience tried to reduce the consensus time a lot, and they were very successful in that, in the sense that now the consensus time is even smaller in some situations than the execution time for the transactions. So a natural solution that a lot of chains right now are using is to execute transactions parallelly. So instead of just executing transactions one at a time, you have multiple cores, and therefore you can execute them in parallel and reduce the execution time substantially. And yes, as I mentioned, a lot of chains have been migrating towards executing these transactions in parallel. Even Ethereum has on its roadmap access lists which would parallelize the transactions. But here's a question for you. If you consider these two cases where there are two transactions in which the first one, transaction one, is not parallelizable, is parallelizable, and you can execute anything in parallel with it, and another transaction that equally uses all the resources but cannot be parallelized with any other transaction, should these two transactions pay the same fee? Well, the answer that the previous work, and I believe, is no. It is using more resource in the sense that if you're not able to execute transactions in parallel to it, then you're losing out on the compute power, and therefore TX1 should be priced more in the second case. So let me go into the model of how we will be defining this. So transaction is basically any set of instructions that would go into a blockchain, and blockchain is basically a world computer in which you can execute all transactions any way you want. And each transaction tries to access like some sort of a data, and basically anything that it reads, modifies, and creates is called an object. And then there are some other parameters that we require for fee determination, which is how much compute time is this transaction going to take, a bound on that. How much am I willing to pay for this particular transaction? Do I have some sort of a priority that I can multiply the fee compared to other transactions that are using the same objects? And a read set and a write set. These read set and write sets are basically objects that are read and write, which are identified using at the compile time. For today's talk, we'll not be looking into the read set or the fee priority multiplier until I introduce our solution. And any object that is being used would be considered as in a write set, even if it is in a read set. So without further ado, conflicts are basically now defined as if two transactions are using the same object, and if one of them is writing. Our aim is to design a schedule where none of the transactions that are executed in parallel are in conflict with each other. And therefore, a non-overlapping schedule needs to be created for execution. So what is the scheduler's objective in this situation? A natural objective that I believe and that we will be using would be to maximize the number of transactions that are being scheduled, but weighted by the fee that this transaction is paying. And this would be more of like how the scheduler's incentives are decided. Now, the previous work that I talked about that mentioned also dealing with transaction fee mechanisms for parallel execution used a different sort of an objective where you needed to minimize the time taken to execute all transactions. And that is a very clean objective as well. However, it requires that under congestion, you'll have to stop consensus, you'll have to wait for some time to let the execution catch up to how consensus is going. So let me talk about the first peril, shell transactions, which is basically fake transactions. So let us consider this case in which the transaction 1 was not very parallelizable, and therefore the transaction fee paid by it computed was very high. What this user can do is add a fake transaction that does absolutely nothing for its execution. It's basically a blank transaction, but fill in the core that wasn't being used. And somehow the fee that it is paying for not just its valuable transaction, but also this shell transaction turns out to be lower than what originally it was paying. And a natural gas consumption mechanism, which is similar to a TFM, is basically Shapley GCM. As you can see over here, and I'm not going to go into the math of it, but with and without shell, you can reduce your transaction fee substantially as a user in this Shapley GCM. And it's not just Shapley GCM that's vulnerable to shell attacks. Multiple of the previous work's mechanisms are actually vulnerable to these user shell attacks. However, user is not the only person in the system. There's also the scheduler who's trying to get as much revenue as possible. So in such a case where it has opportunity to increase the make span, what the scheduler can do is also add a fake transaction such that the make span of the transaction of the schedule increases. By increasing the make span, you're increasing what the transaction 1 is paying or any other transaction in the system is paying and earning a higher revenue. And assuming that there is no burnt fee, there is no cost associated with this attack in the sense that you can just introduce any of these transactions, you'll receive back whatever you're paying, and therefore almost all of the previous work's mechanisms were vulnerable to such a scheduler shell attack, assuming no burn fee again. So is that it? Well, not really. There's another peril that I've not even touched upon, which is uncertain execution. When a transaction is sent, its execution is not really well defined. It depends on the state at which it is going to be executed. So consider this AMM swap example where, as a user, you would read a price, you would check if the price is greater than the threshold, and if and only if it is greater than the threshold, you would go for the swap. And if not, you'll not use the objects of touching the liquidity of the AMM or updating your own balance. So what exactly is the resource usage over here? Should transaction 1 be represented as O1, O2, O3, which were the objects it declared? Or should it be O1, which was its actual usage of objects? Well, since we have a scheduler who cannot really execute each transaction and find out its actual usage, we have to consider TX1 and TX2 to still be conflicting at scheduling time. So now the question arises, should the user pay for these unused objects or the compute that did not get used? According to Ethereum, no. If in Ethereum, you only pay for whatever you're using, whereas in other systems like Monad, you do pay for everything that you declared. So let's define some terms over here. So if we have, we want to determine the fee for transaction 1, you can charge them for all the objects in the world, or you can charge them for only the objects that it is using, or you can charge it somewhere in between. The green part, which is the fee that if we are only charging the users, is an ideal scenario for the users, and therefore we'll be labeling it as user ideal. But then there is this user risk and SR, UR and SR that I have, which is basically user risk and scheduler risk. So user risk is basically the charge that the user is paying for any resource that goes unused. And scheduler risk is the loss in revenue for the scheduler due to these unused resources. Now you can see, as we have over here, the resource wastage is constant. So the sum of the user risk and scheduler risk remains constant given no burn fee. So what this does is actually makes the contingency much, much cheaper. Or the shell attacks that we had is basically made much, much cheaper because the user can now introduce transactions that seem to use a lot of objects, but then just fail and do not pay anything, pay close to nothing if we have a mechanism that is more beneficial towards user. So all the previous works mechanisms over here are vulnerable to contingent shell transactions. Now note over here that in the weighted area, I have a subscript because it's weighted area in the sense that the price is determined before the actual execution of the transaction. It's based on the history of transactions that come in. And therefore, like the attacks over there are a little different. They require a long-range attack in the sense, as a scheduler, I can introduce transactions in a previous block, hoping that in the next block, the fee would increase. So our mechanism is actually, OK. So there are a few questions that need to be answered before we can actually go into our fee mechanism, where first, as I had mentioned, the user risk and scheduler risk. Should the transaction pay only for the objects it's using? Should the user pay for all the declared resources, or should it pay somewhere in between? Our model would deal with somewhere in between. It would try to find out an ideal spot after which we can be shell-free. And how much of this paid fee is actually going to be given to the scheduler in the sense that how much should be burned and how much should the scheduler receive? Because if you burn everything, then the scheduler has no incentives. But at the same time, if it does not have any incentives, then the scheduler risk just becomes 0. And then there is the problem of determining the ideal schedule. There are two objects, there are two transactions. One that uses a lot of objects, but does not promise to use them. It can under-execute. Whereas if there is another transaction that just says, I'll use all the objects in my declared set, then as a scheduler, should I choose transaction 1 or transaction 2 when scheduling, if the choice is between those two? So the scheduler's choices could be optimistic or pessimistic, or there could be a utility function defined in between those two. We did sidestep determining schedule in our work because, again, like if you have weighted area, you can actually not care about the schedule since you can only look at the historical evidence of how parallel your transaction is going to be. So let me talk a little bit about the DFM, which is the object-weighted DFM, which is very similar to the weighted area mechanism previously proposed, except it has limits to what the weighted area or some parameters need to be. So every object carries its own price, and for every used transaction or used object, it pays the fee that this price says. And then if it does not use the particular object, then you would pay some alpha fraction, which is the risk factor of where you want to be. If you want to be Ethereum-like, you would set alpha to be 0. If you want to be in the other direction towards what Monad has, you'll set alpha to 1. So to prevent long-range shell attacks, basically the shells did not really vanish. The price was already fixed by history, but you could manipulate it if the scheduler is constant throughout blocks. But the cost that this particular scheduler would be incurring would be the burnt fee for this transaction. Since gamma fraction of fee is retained, anytime a transaction is sent, 1 minus gamma times the fee that it pays would be burnt, and that's the cost incurred. As long as this cost is larger than the theoretical maximum revenue, object-weighted DFM is safe. And we show the parameters in our paper. So in summary, we gave a formal model for parallel execution and how contingent resources should be modeled. And we gave an impossibility, which is that the user risk plus scheduler risk must be a constant, and somebody in the system, either the user or the scheduler, would lose out. And finally, the object-weighted DFM, where we have the parameterizations that are required for shell-proofness. So there are some things that we still need to do. The first being the scheduling algorithm. As I said, we completely sidestepped that because by analyzing per object pricing based on history, I did not need to compute how parallel the particular transaction is compared to its peers. And the fee can be determined before the schedule itself. In other mechanisms like what previous work had, like time proportional make span or the Shapley-based mechanisms, the schedule as well as the transaction fee mechanism both interact with each other, and working on those two together is going to be going to give results that are much better. And secondly, we completely avoided concurrency control by not executing transactions that had any conflict. But there are methods in which, like, for example, you can schedule the transactions early, and then if there is a failure of a transaction, then you can execute some backup transactions that you can have, so some sort of an online rescheduling mechanism, which could conflict with the transactions that are already being executed but are given lower priority. Or alternatively, you can do some sort of an optimistic execution like what Monad does, and then compute how, like, And finally, there is a trade-off that's due to the caching of objects that are being used. So if there are two transactions using the same objects, then the second transaction can actually be executed faster. And therefore, there is a point to be made about this particular transaction being priced less, or both transactions being priced a little lower. However, this is directly in conflict with the parallelization, because two transactions that are using same objects are not parallelizable. So that's all, and feel free to contact me and any questions. Thank you.
So for most of this talk, if not all, You basically talked about what is called static transactions, where you know up front, okay, all the addresses that you're going to access. This is, I don't want to say non-realistic, but I mean it's realistic for many use cases, okay? But in general, you're writing with a program that is, tune compatible, then you may not know it, you may not even have an estimate, okay? You may have a tree of like 1 million, accounts, and on average you will, you will do a log-in operation to get to your account. And in some cases it's going to be much long, so are you concerned about these cases at all, or that it's not?
Yes, so great question. If I understand the question correctly, the question is that when you're executing the transactions, you don't really know the objects that are going to be accessed. In the move language by Solana, what happens right now is you can compute all the objects that this particular transaction can possibly touch. And then when you're executing, yes, you don't know the objects that are actually going to be touched, but that is the second peril that I was talking about, where when you don't know what this transaction would actually execute, what objects it would actually use, then you'll have to price it based on its actual execution, but also pay some resource. Or the scheduling would happen based on all objects, whereas the pricing must happen based on the actual minus and also the total objects that are being used, if that. Yeah.
Maybe I have one more question. So there's a bit of a fundamental tension here between when you're wanting to execute things in parallel, you love that they're touching very different state. But for reading from storage, it would be great if everyone just reads the same state to some extent.
Yes.
Have you thought about this, or how could you adapt maybe what you've been working on to also account for that?
Yes, that's a great question. Again, one of the things that I was mentioning in that needs to be done is finding such opportunities and actually modifying the TFM to have a better efficient object usage. I haven't completely I don't have an exact thing that I can say about yes, it should reduce the prices definitively, but yeah, that's a good question, and I don't think.
Okay, so if there's no more questions, this concludes the DeFi session and also the day. Let's thank our speaker once more and have a good day.